What's up, CoderByte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and today we are going to be continuing the conversation all about graphs. Particularly, we're going to be talking about depth-first traversal. If you haven't seen our other videos in this series where we went over the different sorts of implementations of a graph in code and the other kinds of traversal, breadth-first search traversal, make sure to go check those out as well. So, what will we cover in this video? We're going to go over the actual traversal method. We're going to talk about the algorithm and the data structures that the algorithm uses to be able to make the traversal happen. We are going to go through a code implementation of the traversal. And finally, we are also going to be solving a real-world interview problem. Of course, most interviewers will not just ask you to traverse a graph, right? They're going to ask you some sort of question where you're going to have to apply your knowledge of all of the different sorts of traversal methods and solve the problem using the traversal, usually with a little bit of a catch. So we'll be sure to kind of talk through various scenarios, when this traversal is useful, etc. As with breadth-first traversal, depth-first traversal is just referring to the order in which we visit the nodes. So for this algorithm, we go deeply into the data structure. We continue to go further and further down into the graph until we either reach the node we're looking for or we reach a leaf node. A leaf node here means just one of the outer edge nodes where the only other adjacencies to it are is its ancestor, right? The one you came from. Otherwise, it's at the edge of the graph. At that point, we backtrack back up the graph until we reach another spot to continue to traverse down. I'm going to just walk you through the ordering here just so you can picture this before we talk more about the algorithm and how we'll do this and accomplish this in code. So let's say we want to start at the Dallas-Fort Worth airport, right? So in depth-first traversal, same as the other traversals, we're still going to take one of its adjacencies, right? So let's take LAX to start. Now, this is where it changes. Instead of also visiting JFK in this iteration of our algorithm, we are going to continue down, right? We are going to continue to traverse the graph deeply until, like I said, we reach the node we're looking for or a leaf node. So from LAX, we go to Honolulu. Okay, Honolulu looks like a leaf node, right? The only other node it's attached to is the one we came from, LAX. So we backtrack. We go back up the branch that we came from, and then we continue down. In this way, we will visit all of these branches before we ever even get to this whole part of the graph. So here we have LAX. Let's go to San Francisco. And then from San Francisco, we can go here to Hong Kong. And then we've reached another end, right? We've reached another leaf node. So we backtrack and we backtrack again, right? Because San Francisco doesn't have any other nodes to visit. And then we go to Newark. And this is sort of, etc., right? This continues for every branch in every branch that the graph is made up of. So once again, for this algorithm, we traverse deeply into the data structure. We explore all of the nodes on a branch going forward until you either reach the node you're looking for or a dead end. Keep those in mind because, hint, hint, we are going to be using recursion for this. And remember, if you've seen our recursion videos, you need to know your base cases. So remember that we want to stop the algorithm, right, when we've reached the node we're looking for, or we've reached a leaf node. Once we've reached that leaf node, we want to backtrack up that branch until we reach a new branch to explore. This uses a stack data structure. If you haven't heard of it, a stack data structure functions exactly like a stack of plates or a stack of books. Once you put the data in, when you add something to the stack, it becomes the last data to come out, right? If you're stacking plates, the first plate you put down will be the last plate you take off. This is called first in, last out, as opposed to a queue, which is first in, first out, right? I'll show you in a second how we are able to use the stack to affect the ordering of the traversal in a second. Okay, so let's go through this with a stack and kind of pseudocode it out. So before we implement it, you can imagine what this is actually going to look like. So I'm going to go ahead and I am going to start with my stack here. And let's say we're starting with Dallas-Fort Worth, as we like to do here. So I've just added that to the stack, right? So according to this algorithm, we are going to begin to visit Dallas-Fort Worth's adjacencies. So let's go to LAX, let's add LAX to the stack. And instead of going to JFK now, we are going to continue down these other branches deeply into the data structure. So let's go to Honolulu, right? Now, Honolulu is a leaf node. So what do we have to do? We have to backtrack, right? We have to go back up the branch until we have another branch to continue down. So Honolulu is done. We can pop that off the stack. And then we're back to LAX. Now we continue to add LAX's adjacencies, right? So let's add San Francisco. And then let's add Hong Kong, right? Now we've reached another leaf node. So we can pop that off the stack. And San Francisco also does not have any other adjacencies, right? So we're done there as well. So we can pop that off the stack. Finally, we're back to LAX. That has more leaf nodes still to visit. Let's add Newark. And so on and so forth. So because of how we are adding and taking out data from this data structure, I hope it's clearer how the algorithm backtracks along the stack and is able to continue to traverse deeply when it hits a dead end. It's implementation time. So as you can see on the screen, I have some boilerplate node and graph classes you might recognize from other videos in this course. I have some classic normal methods that you might use on the graph, such as get adjacent nodes and is connected. And in this particular implementation, I am using an edges list. This means that every node will have a reference to all of the nodes that it is connected to, aka a list of all of its edges, right? So you'll also see that I have filled out all of the airport data here as nodes and gone ahead and connected all of the ones that are connected to mirror the graph that you see on the screen. And this will set us up to be able to deeply traverse this graph and see what we can do. So let's start with taking this depth first traversal method and talking about its function signature. So we definitely are going to want to have a start node, right? Because whenever we're traversing a graph, we're going to start somewhere. And of course, we're looking for something, right? So let's pass in that end node. And that's going to be the graph that we're looking for. Now, let's do some pseudocode first. The algorithm goes as such, right? Keep traversing deeply, right? Keep going deeper and deeper into the graph until you either hit a leaf node, which is a node that is at the edge. It doesn't have any other adjacencies except for the one from which you came, or you are at your end node, right? You've found the node that you've been looking for. Now, I said this before, but in case you're, thinking about this right now, this sounds like a recursion problem, right? These kind of sound, until you do this or this is almost, they're your base cases, right? And we're essentially saying we want to continue to depth first traverse on those adjacencies until we hit either of those base cases. Now, one of the nice things about using recursion here is that instead of actually managing a stack and pulling and popping off of it, we can just use the call stack, right? Because the call stack functions in the same way. It's a stack just like an array would be a stack that we would implement ourselves. And because of this, we can kind of offload all of that onto Node.js, right? So let's code this out. So our first things we want to do is actually code out those base cases, right? So our two base cases are as follows. If the start value is equal to the end value, right? That means that wherever we are, we've found where we're going, then we're good, right? So we can probably, console.log found it, right? Found the node, and just return. And that is going to be one of our base cases. We have found the node we're looking for. So what's actually happening when we hit that base case? Well, we're returning from a function. And in JavaScript, when you return from a function, you are popping off that call stack, that call frame from the call stack, right? That's the act of removing it. Now, I said that we were going to use recursion and that would allow us to use the call stack as the stack that is keeping track of the nodes that we're visiting, right? So what does it mean to visit a node? Well, really it just means to call this function, depth first traversal, with that node as the start, right? That is the act of visiting a node. That node is the start, and it is going to continue to be we are going to continue to traverse down its adjacencies. So let's loop over those adjacencies, right? That's going to be the same in any traversal. Adjacency of that edges list of that start node, right? And essentially, what we want to do really is for each of those adjacencies, we want to call depth first traversal on it with it as the start, right? So what that will do is the call stack, will manage the ordering of visiting the nodes for us. And I'm going to try and show you this with a debugger. I don't know if any of you guys have used this debugger before, but it's something that I personally really like to use when I'm learning something or, of course, debugging. So we can kind of watch this happen. So we can watch the stack grow and shrink with each visit to the nodes. But for now, let's just call this method with the adjacency as the new start. And of course, we only want to do this if we haven't seen that adjacency yet, right? If we haven't visited that yet. Now, in our breadth first traversal method, we just initialized a set and we checked against that set. For this method, we're going to want to keep track of what we visited, and we're going to want every single function call to be aware of that, visited, right? We're going to want every function call to know if any other function call visited that node, because then we're not going to want to visit it. So the only difference here is that we're going to want to keep it we're going to want to have it be a parameter to the function. This is going to be the visited set. And essentially, we are going to continue to pass that as we recurse so that every call knows what has been visited and what has not been visited. So of course, here we can only do this if visited doesn't have this adjacency in it, right? So let's move that up. And the other thing we are missing is actually adding the adjacency to the visited set, right? So let's do that up here. So that way when we're visiting nodes, they will always be added to that visited list, and we can continue to pass that down. And let's see, that is actually it. I believe that will do it. So let's also just log out what that start is so we can watch the algorithm go. And we can say this is visiting node, right? Because what we're doing is every time we call the function, we visit that node. And of course, you may be wondering, Elizabeth, you said there were two base cases, right? Not only if we found the node, but if we reach a leaf node. If we're at the end, we'll have to backtrack, right? So what that means is we have gone through all of those adjacencies, right? So in our function, you can imagine in this for loop that we've done every adjacency, right? We've gone through them all, they're all visited, we're at the end. The function will come here, right? And here is where our final base case lies, which is we've reached the end. We've deeply traversed the entire branch. And we can implicitly just leave this as an undefined return because we don't care, right? All we want to do is make sure that that stack frame gets popped off, which it will, even if we return nothing or undefined here, right? So I hope that makes sense. Again, we'll go through this with the debugger, so hopefully you'll be able to kind of see how that's actually happening. But let's first log out some of this. Let's see. So let's see what happens when we run this. Visited.add. Oh, that is because I am not passing in that visited, right? Because we have to initialize that somewhere where we're going to keep track of each of the nodes. And what would actually be better is instead of adding that there, I am going to say up here, if there's no visited, right? If someone started this without giving me a visited, initialize one, right? So I'm going to say visited equals a new set. And that way we don't rely on the caller to, define the data structure that we're using. We're going to define it ourselves and start to pass it here, right? Okay, so let's see what we get. And all right, so it looks like so far so good, right? We start at Dallas Fort Worth and we go to its first adjacency, LAX. And then from there we continue deeper, right? We go to Honolulu. Honolulu is a leaf node, right? So we backtrack back to LAX. We then visit Newark and we backtrack again, right? Because Newark is another leaf node. We go to San Francisco and we continue on we get it, right? We get it right down here. That's the Hong Kong. And then here's just the continuation, right? This is the way I wrote this is that the traversal will continue to, we're not finishing here, right? We've initialized the whole stack and we're going to depth first search the whole entire graph. I want to make sure you guys visualize that stack because that really is the core of this algorithm. So to do this, I'm going to be using the debugger that comes with my Visual Studio Code editor. And you can really do this in any debugger, the Chrome debugger or whatever. But this is a debugger that I find super useful and pretty easy to set up with a regular JavaScript file. So to see that debugger in Visual Studio Code, you can go to the debugger tab in the sidebar. You can actually just click run and debug. And when I click that, I'm going to choose Node.js because this is a JavaScript file. And that's basically it, right? So super useful tech tips, for you guys. But here you see in this debug console exactly the consoles that we were seeing before. What's super fun and valuable, of course, though, with debuggers is adding those breakpoints. If you haven't used a debugger before, when you add a breakpoint to your code, you're essentially just giving a signal to the engine, hey, stop running the code at this point. I'm going to inspect and see what's going on. That gives you the ability to look at variables and figure out the state of the function while it's executing before it actually finishes. So for us, I am going to add a breakpoint, pretty arbitrarily here at the beginning. I'll add it before this loop. And that way we'll be able to kind of see what is this call stack look like, what is start, what is visited look like, etc. So I'm just going to run this again and click node again. And you'll see here in this side area, that we have some local variables, and here is our call stack, right? So here's our first call to depth first traversal, where start is DFW, which makes sense. That's our first call, as we said. End is Hong Kong. That's going to stay the same. Visit is undefined, so we're going to initialize that as a new set. And yeah, so that all looks good. So again, if you haven't used debugger before, here are some of the functions that you can call while you're in this paused state. So here I'm going to just click step over, which will basically just continue to, go line by line until we either click continue, which will continue the execution until the next breakpoint, or it returns and stops. I'm just going to step over for a few, steps just so you guys can kind of see what's going on. So you'll see we skipped this, this little bit because we're not at the end yet. And we're logging right now that we're visiting DFW. And here's the line where we add the Dallas-Fort Worth Airport to visited. So you'll see in this sidebar here that visited now has one entry, and it's a node, and here it is, right? It's the Dallas-Fort Worth Airport with its edges. So I'm just going to continue here. And you see, here's the first spot where we add something to the stack, right? We are going to add, let's see what that adjacency is. So the adjacency LAX, we are going to add that to our stack, right? Because we haven't visited it yet. So let's continue. And here is where we are building our stack, right? This is our call stack. This is essentially the same as in those slides where I was adding to that array, and I was just pulling and popping off of the top of the stack as I visited the nodes. So right here, this is the stack, and I think that this is super important to understand when doing any sort of depth first traversal, that there's no magic. You don't have to manage a stack by yourself because the call stack does that for you. So let's continue. Continue again. And here we go. This is another call to depth first traversal with the start at Honolulu. So this is again building the stack. And the thing that I want you to see is what happens when we pop something off the stack, right? What happens when we meet one of our base cases? So here we go, right here, right down here. And remember, we said that implicit return of undefined is one of our base cases, right? That means that we've reached an edge of the graph or a leaf node. In this case, we're at Honolulu, right? And we know that Honolulu is a leaf node. So I'm going to step over again, and you see that call gets popped off of the stack. So, this is something that I found super useful when learning this algorithm, visualizing exactly what's happening in this algorithm and where exactly the management is of the order of the nodes that we're traversing. As always, it's important to consider the time complexity and space complexity of any algorithm. So, what is the big O of depth first search? If you think about it, even though it's recursive, we are always only visiting every node one time, right? So you know that the time complexity will be that the algorithm will run at least the number of vertices in the graph. You can also imagine that with every single function call that there is to visit a node, what it means to visit a node is to add all of its edges to the stack, right? All the edges that haven't been visited yet. So for every node, you're also going to kind of iterate for every edge. So for this algorithm, the big O will be a big O of V plus E, where V is the number of vertices and E is the number of edges. The space complexity is a big O of V, where V is the number of vertices, because at most we will store every vertex, right? If the entire graph is just a linear graph, the whole entire stack, which is what we're using, right, as our data structure to determine where we're going in the graph, it's at most going to be all of them, right? All of the vertices. And to visualize this, you can always bring up that call stack that we just saw in VS Code, right, with that debugger. At most, that call stack is going to be the number of vertices in the graph itself. So that's how you can think about the space complexity of this algorithm. So what kinds of interview questions is depth-first search good for? One of the things that it can help you with is to detect a cycle in a graph. I visualize this kind of as a yo-yo. I don't know if anyone else will, understand at all what I mean. But basically, when you're traversing down into a graph and you're going down a branch, right? You can imagine that if you have a node that's already in that branch, if you reach it again, that means that there's a cycle, right? At some point in that branch, something points back to that original ancestor, which is essentially a cycle. So if you just do a depth first search, as soon as you reach a node again, you can basically return, yes, there is a cycle here. Another thing that it's useful for is determining whether a graph is bipartite. Now, I don't believe we've talked about this term yet. It's something that I think is a more advanced topic, but be sure to check out our future videos. I will definitely be making a video all about interview questions that have to do with this bipartite idea. But a bipartite graph is essentially just a graph whose vertices can be divided into two independent sets, such that every edge connects the vertices in the first set to at least one in the second set. So that's kind of hard to imagine with words, but here's a picture where you see you have a graph here, and you are able to divide the vertices into these two sets where every one in the first set has a connection to something in the second set and not a connection to any of the ones in its own set. So this is useful for different kinds of things, and we'll talk more about this in future videos. Another thing depth first search is good for is finding whether there's a path at all. So breadth first search is really good for finding that shortest path, but finding whether or not is there a path at all, depth first search is an excellent method, right? And for this one, you can kind of think of a maze, right? Where you're trying to see, can I get from point A to point B through these various twists and turns? When I reach a dead end, I need to backtrack and then continue on, right? That's a classic maze question. And if you are just looking for whether or not it's even possible to get from point A to point B, depth first search is a great algorithm for that. The other thing that it's really useful for is this idea of topological sorting. Topological sorting is a concept basically just that every node in the graph will appear before all the nodes that it points to. So this only works, of course, with a DAG or a directed acyclic graph. You can imagine this only working for that because number one, it has to be directed. Otherwise, you couldn't put one node before another because they each point to each other. And it also has to be acyclic because in a cyclic graph, there are going to be ancestors that are also children, right? That's the nature of a cycle. So you couldn't order it in this way. We're going to go into more detail in a second with this idea, this topological sorting. So let's do an interview question. Given a DAG, return the topological ordering. So here's an example of a graph. This is a directed graph. This is also something new that we haven't actually coded out yet together using this concept of direction with the connections between the nodes. So you have these 6 nodes all connected, and the question is to return this topological ordering, right? Give me an ordering such that no node that a node points to is before it in the list. So for this question, some valid answers would be A, E, B, D, F, C. And let's go over why that is a valid ordering. So we see here, if we go through these nodes, I'm just going to draw directions to the nodes that they have as their adjacencies. So let's start with A. A has an adjacency B, right? So we see that like that, and it has an adjacency C. So let's draw that like so. Okay, so B has an adjacency to D. Oop, this is going to be a tough one to draw with this thick marker. D is going to have an adjacency to F. F has no adjacencies that it's pointing to, right? C has no adjacencies that it's pointing to. And then finally, E has the adjacencies C and also F, right? Now, obviously, this drawing is not clear at all, but you can see the direction of all the arrows, right? All of a node's adjacencies are in front of it somewhere in this ordering, and that's what we call a topological ordering. Obviously, there can be different orderings where that is still true. So this is also a valid ordering for this graph, EACBDF. And go ahead, do that same exercise, draw those arrows, and prove to yourself that all of the nodes that a node is connected to are in front of it in this ordering. Before we code this interview question together, I want to go through the algorithm that we're going to be implementing first with some diagrams and some pseudocode to help you visualize what's happening when we actually get to the coding portion. So you remember topological ordering. We're tasked with returning the nodes in a list in an order. They should be ordered such that any node's adjacencies always come after it in the list, right? So what does that really mean? So let's walk through this together. If you follow the nodes, let's say starting from node A, right? And you go to the node that it's one of its adjacencies that it's pointing to, B, and then you continue down to D, and then you continue to F. A, B, D, F would be a valid topological ordering for the graph A, B, D, F, right? Forget about C and E. Depth first search, by nature of just continuing deeply into the data structure, returns a valid topological ordering. The difficulty here, or the complexity, will be combining those various depth first traversals so that the topological ordering still is maintained for the entire graph, for all of those various branches, right? So that's number one, the thing I want you to think about is we're going to be doing a bunch of depth first traversals, all from different entry points into the graph. And then somehow we're going to need to combine them such that the ordering maintains that topological ordering, even after we combine the various branches. So how are we going to do that? So I'm going to start us off here. So let's say this is our array, right? Our ordering. And we want to return this ordering. So we start at A, we visit A, okay. Then we go to B, right? And then we go to G, and then we go to F. Okay, F is an end, right? An end of sorts. So it's not going to necessarily have anything after it, right? So it needs to go at the end of this, initial ordering. So let's put F there. We go back down to D, and we can add D. We can prepend it right here, right? And then we can go to B. Great. We backtrack back up to A. And what happens here is that we can't put A in before we put C in, right? Because that would mean that C would be before A, and A points to C. So that's not legal. That's not valid. So instead of backtracking and adding A, we continue to add the other branches. So here in this case, this would be C, right? So we add C here. Finally, we're at another end, so we backtrack back up, and only then do we add A, because we've added all of its children. So that's where we can add A, right? Now, what do we do with E, right? When and where do we put E? So as I said, we're going to be kind of starting different depth first traversals down from different points of the graph. So what would happen if we started one here? So we visit E, right? Now E definitely can go before everything, right? Because we haven't reached it yet. So therefore, it wasn't after any of the other nodes we've been to. If it was, we would have already gotten there in our depth first traversals, if that makes sense. So we can safely add it to the beginning of the list, right? And I'm going off screen here, but imagine that the E is right there. So that E now still comes before F and it still comes before C, right? But it can come before A because A doesn't point to it. And so what I want to kind of show you here is that this is how we do this depth first traversal. And we actually pretty closely follow that stack, right, as it grows and shrinks. And we want to add the node to the ordering when it is completely visited, it has no more adjacencies, right? Because that means we've already added all of its children, so it's safe to add it. Only at that point do we want to add it to our list. And essentially, as we depth first traverse from various points in the graph, we add all of the unvisited nodes, we prepend them because we know that if we haven't gotten to them yet, that means that they don't need to come after any of the other nodes that we visited. Let's code this interview problem. Okay, so you'll recognize this, again, boilerplate node and graph class that I've been using throughout all of these videos. The only difference to note here is that in this connect method, we haven't yet worked with an actual directed graph in code, right? So how are we going to make it a directed graph? It's pretty easy. Before this, we were not only pushing the node that we passed into the instance that's calling connect, but we would also push node.edgeslist.push this. We would do it in a bi-directional way so that they would each have each other as adjacencies. To indicate direction, all we really have to do is not do that, right? So when you connect something, it is only one direction. You are only adding an adjacency of what you are passing to the calling node. If you want to, add a different connection or an adjacency, whatever, you have to explicitly do that. You don't get that bi-directionality by default in this method here. Okay, so I've gone ahead and filled in the graph data to mirror the graph that's on the screen. And what we want to do is implement this topological sort, right? So I'm going to take that and let's start talking about this function. So if you'll remember from the slides, we want to be able to we want to construct a bunch of depth first searches, right? We want to construct depth first search from basically every entry point to the graph that there is. Essentially from every node on the graph, right? So our graph does have this, this dot nodes property. So I think what I'm just going to do is I'm going to loop over that, and I am actually going to probably call depth first search on each one of them. We haven't written that method yet. We will in a second, but just to give you kind of a preview of where I'm going with this. Okay, so for const node of this dot nodes, and what do we want to call it? Depth first traversal. And we want to call it on that node, right? And that is just going to be a function here. And it's going to, just like our other function from our, a little while ago, it's going to take a start node and we're going to do some traversing. So before we do the depth first traversal, we're obviously going to still have to keep track of the visited nodes array, right? We don't want to visit any nodes multiple times. Here, though, instead of having it just be managed within the depth first traversal function, we actually want all of these calls, right? Every single time we call depth first traversal from all of the different entry points in the graph, they each have to know about each other. So we don't want depth first traversal to manage that visiting nodes array. We actually want the topological sort to manage that visited nodes array because it's still not, we don't want to traverse any branches needlessly. So to do that, we can just initialize a set, just like we've been doing. And we can pass that in here. So that's one of the differences that you'll see immediately. Okay, so we have this idea of, visited set, right? And topological sort is keeping track of all of the different ways we're kind of entering the graph, and then we're going to start the depth first search, or the depth first traversal. So right away, we can, right, if we have already seen this start node, we can just return. Don't do it. Just forget about it, right? Okay. So if visiting nodes doesn't have it, right, what do? We add it. So let's do that right here, visited.add start. And then, like before, we're going to loop over those adjacencies, right? And essentially, this is all the same, right? We are going to call this method with that adjacency as the start node and visited as the set, right? Okay, so this should all look pretty familiar to you guys. And this will actually, as far as traversing the entire graph from all of the entry points, this will do it. And we could even log out here. And we can see what we get. Okay, so we start at A, we go to C first, we backtrack back up, then we go to B, then we go to D, then we go to F, and then we finally visit E. So that does make sense, right? We are traversing from all of the different possible spots to get in on the graph, and it's doing it in depth first ordering. So that's great. So now the question is, how do we get this topological ordering? So we saw in the slides that we only want to add things to the ordering when they have been completely visited, right? We're at the end. There's nowhere else to go. So, of course, that happens where in this function? That happens at the end of this for loop, right? That means that we have visited all the nodes adjacencies, and we're just about to pop it off the stack, right? So that's going to happen right here. About to pop start off the stack. And popping it off the stack signifies that we're done visiting it, and we've actually visited all of its children, right? So it is at this point that we want to put start in our ordering, when we're done traversing it. So remember, if we go back to our example graph here, we put F on, we put D on, we put B on. We don't put A on until we've finished A's for loop, right? And as far as A is concerned, we still haven't visited C, which would have to be added to the ordering before A because A points to it. Only when we've completely gone through all of A's adjacencies are we ready to put A in that ordering. And that will be the valid ordering, right? If that makes sense. And because each branch we can just prepend to the list that we're maintaining, because again, if that node needed to be ahead of something, we would have already seen it because of depth first search. We can just start prepending things to the stack, right? And in that way, we'll get this valid ordering. So what we'll need to do is we'll have to pass in some sort of data structure to keep track of these things, right? The order. So I'm going to do that up here. I'm going to say const ordering, top ordering, right, is an array. And we're just going to pass that in, right? Because we just want to maintain the one ordering. So here we're going to get the top ordering. And basically all we have to do is just push, right? Push that start. I'm going to push the value just because then we can log it out easier. We just push that start value that we've traversed all its children, just put it in the list, right? Now, of course, we said we were going to prepend, right? So at the end of this, I'm just going to reverse that here. So I'm going to say console.log top ordering.reverse, right? And that will give us the ordering. So let's go ahead and see. Okay, can't read property push of undefined. So we got, oh, because I'm not continuing to pass it down. There we go. And do we get a valid ordering? E, A, B, D, F, C. Let's see. E points to F and C. That looks good. A points to B and C. That looks good. B points to D. That looks good. D points to F. That looks good. And of course, there's C, which things point to. It doesn't point to anything. So that is a valid ordering, and I hope that kind of made sense how we are tracking these things just by pushing onto this array as we're about to pop something off the stack. That's what we want to capture, right? The thing that's being popped off the stack as, okay, we visited all of your children, you are safe to be added to the ordering because all of your children are already added to that ordering. So we're done for today. Thank you so much for coming and learning all about depth first traversal with me. This is actually one of my favorite algorithms. It took me a really long time to really understand, and I hope I was able to explain it a little bit, better for you guys so you get to understand exactly how the traversal happens, how the recursion happens, and then how to apply it for actual interview problems. Just to sum up, we talked all about the depth first traversal method. We talked about the big O, time complexity and space complexity of this algorithm, as well as actually going over an interview problem, topological sort, where you have to kind of use depth first traversal with a little bit of a catch. Next week, we're going to be talking all about more interview problems with graphs. There are many of them. We're going to talk more about that bipartite idea and some other cool stuff. So be sure to check out all of our future videos. Thanks.